So, imagine opening the door to a massive, totally windowless server room.
Okay, setting the scene.
Right. And inside there are like billions of wires, pulsing lights, intricate cooling systems, and millions of tiny switches that are just flipping thousands of times a second.
Sounds incredibly chaotic.
Exactly. And if someone asked you to map out how a single email travels through that room, you would probably feel, completely overwhelmed.
I mean, yeah, most people would. But underneath all that apparent chaos is a highly logical, fiercely optimized architecture. You really just need the blueprint.
And today, we are handing you that exact blueprint. Welcome to today's deep dive. We were using Dr. Todd Vanderah's book, Nolte's Essentials of the Human Brain.
It's an incredible resource.
It really is. And our mission today is to strip away the intimidation factor for a highly focused medical review. So whether you're a medical student, a young professional, or just an intensely curious self-taught learner, we are building a functional foundation of human neuroscience for you.
And we should mention the guiding philosophy here.
Right. Albert Einstein is actually quoted in the preface of this book saying, "Everything should be made as simple as possible, but not simpler."
Which is perfect. We are definitely taking that to heart today.
Wow.
We won't shy away from the real medical terminology, but we will focus heavily on those underlying mechanisms.
So keeping it clear but accurate.
Exactly. And to understand the whole system, the absolute best place to start is the fundamental unit of information processing, which is, the neuron.
The basic building block.
Right. Despite coming in all these various shapes, neurons share a core anatomical theme built for communication. The cell body acts as the manufacturing plant, basically synthesizing macromolecules.
Okay.
Then extending outward are the dendrites, which receive incoming signals from other neurons, and a single long axon that conducts electrical signals. Those are action potentials away from the cell body.
And the speed of that conduction relies really heavily on myelin, right? That fatty covering wrapping the axon.
Yeah, precisely.
Because I used to think of myelin simply as rubber insulation on a copper wire, like just to keep the electricity from leaking out. But the text explains it as a much more active mechanism. It creates what's called saltatory conduction.
Yeah, that insulation analogy is super common, but it's a bit too simple. The signal doesn't just flow smoothly down the axon. It literally jumps from node to node between the myelin sheaths.
Wow, it actually jumps.
Yeah, and this jumping mechanism drastically accelerates the transmission. And that myelin isn't just, inert fat. It is actively created and maintained by glial cells.
Which forces us to look at the nervous system's geography, right? Because the text divides these glia based on where they actually live.
Exactly. Location is everything here.
Right. So in the peripheral nervous system, meaning the nerves extending into your limbs and organs, Schwann cells do the myelinating.
Yep. Schwann cells are the peripheral workers.
But in the central nervous system, so the brain and spinal cord, the entire support crew changes completely.
It really does. In the central nervous system, oligodendrocytes take over the myelin production. But you also have a whole suite of specialized glia in there.
Like a whole different maintenance crew.
Exactly. You have astrocytes, which maintain the chemical environment and form the blood-brain barrier.
So they decide what gets in and out of the bloodstream.
Right. Then you have ependymal cells, and they produce the cerebrospinal fluid that cushions the brain. And finally, microglial cells, which act as the local immune defense, actively scavenging for plaques or damaged neurons.
So mapping this out on a larger scale, this cellular division perfectly explains the gross anatomy of the brain.
How so?
Well, when we talk about gray matter, we're really looking at the processing center, so those dense clusters of cell bodies, dendrites, and synapses.
Ah, right.
And when we talk about white matter, we are looking at the massive communication highways of axons. And they appear white specifically because of all that fatty myelin wrapping them.
That structural hierarchy scales up to coordinate the entire human body. At the macro level, the central nervous system consists of the spinal cord and the brain, which includes the brainstem, the cerebellum, and the massive cerebrum on top.
And one of the most fascinating anatomical quirks the text points out is how this structure actually sits inside the human skull.
Oh, this is such a cool evolutionary detail.
Yeah, because we evolved to be bipedal-like, to walk upright on two legs.
Mm-hmm.
Our brain development had to adapt to that posture.
Right. The embryonic neural tube in humans develops the severe kink to accommodate our posture. It is called the cephalic flexure.
The cephalic flexure.
Yes, and it actually persists in the adult human brain as an 80-degree bend between the midbrain and the diencephalon.
Which is wild, because if we didn't have this bend, our spinal cords would point straight down,
Yeah.
but our faces would be pointing straight up in the sky.
Exactly. Our embryonic development literally holds the physical evidence of our evolution to walk upright.
That is just incredible to think about.
Yeah.
And sitting above that 80-degree bend is the cerebral cortex, right? That wrinkled outer sheet divided into specialized lobes.
Yep. You have the frontal lobe for motor control, the parietal for sensory processing, the occipital at the very back for vision, the temporal for hearing, and the deep limbic lobe for emotion.
But, naming the lobes feels a bit like looking at a map of continents without knowing the trade routes.
That's a good way to put it.
Like, if I touch a ridiculously hot coffee mug with my index finger, how does that raw physical sensation actually navigate the deep brain to reach the parietal lobe?
Okay, so the nervous system creates physical topographic maps of your body within its pathways. This is known as somatotopic organization.
Okay, so a physical map.
Right. When you touch that hot mug, the nerve endings in your right index finger fire. The signal travels up the peripheral nerve, enters the spinal cord, and begins its ascent. And crucially, these pathways cross over to the opposite side of the nervous system.
So the signal from my right finger physically crosses to the left side of my brainstem.
Exactly. From there, it hits the diencephalon, specifically a structure called the thalamus.
Thalamus, got it.
Think of the thalamus as the ultimate relay station. Almost all information destined for the cerebral cortex must pass through specific nuclei in the thalamus first.
And then it routes it.
Yep. It then projects that signal to the primary somatosensory cortex in the parietal lobe.
But what I found incredible about this somatosensory map in the cortex is that it is wildly distorted. Like, it is not a one-to-one physical representation of your body at all.
No, not at all. The map prioritizes receptor density over physical size.
So it's about how much data is coming in.
Exactly. Your fingertips are packed with receptive endings for fine touch. Therefore, the thalamus dedicates a disproportionately massive bundle of nerve fibers just to the fingers.
Makes sense.
And a huge geographic area of the cortex is assigned to process that data compared to, say, a much larger physical area like the middle of your back.
Which perfectly explains why we can read tiny braille bumps with our fingertips, but we absolutely couldn't do it with our elbows.
Right. The processing power just isn't assigned to the elbow.
So the thalamus handles that sensory routing.
Yeah.
And sitting just below it is the hypothalamus, which the text says acts as the control center for the autonomic nervous system, so regulating hunger, temperature, circadian rhythms, all that background stuff.
Yes. And surrounding those two deep structures is a collection of nuclei called the basal ganglia.
Okay, the basal ganglia, what do they do?
These are critical for controlling movement, but they don't simply act as a gas pedal. They act much more like a complex gatekeeper.
Like forming parallel loops with the cerebral cortex.
Precisely. By using these loops, the basal ganglia constantly inhibit unwanted movements while simultaneously exciting intended movements.
Could you give an example of how that works clinically?
Sure. Think of a patient with Parkinson's disease. Parkinson involves the degeneration of dopamine-producing neurons that feed into the basal ganglia.
So the gatekeeper system is failing.
Right. When that fails, the patient experiences resting tremors, which are basically unwanted movements slipping through the gate, and bradykinesia.
And bradykinesia is like a slowness of movement.
Yeah, and extreme difficulty in initiating intended movements because the gate essentially won't open.
Wow, so the thalamus is routing specific sensory data, and the basal ganglia are gating our physical reactions.
You got it.
But here is the piece I always struggled with. If I am deeply asleep, sensory data is still hitting my nerves, right? Like the blanket is touching my skin, the room has a temperature.
Oh, absolutely. The data is still flowing.
But I am not consciously processing it. So there has to be some mechanism that actually boots the cortex up to receive all this data.
There is. That master switch is located down in the brainstem. It is called the Ascending Reticular Activating System, or ARS for short.
The ARS.
Yeah. The ARS is a network that modulates the overall level of cortical activity. It wakes the cortex up, maintains baseline consciousness, and regulates your sleep-wake cycles.
Which introduces a really fascinating contrast in how the brain communicates.
How do you mean?
Well, the sensory pathway from my finger to the thalamus, that's a discrete point-to-point connection, right? Designed to preserve a highly specific piece of data.
Yes, very localized.
But the systems modulating our consciousness, like the ARIS, they cast a massive diffuse net.
That's a great observation. Certain brainstem nuclei use small molecule transmitters, things like norepinephrine, dopamine, serotonin, and acetylcholine.
The famous ones.
Right. And instead of sending a specific pinpoint of data, these diffuse neuromodulatory systems regulate the background activity level across enormous regions of the central nervous system.
So they're carrying a specific message like hot mug.
No, they operate using slower second messenger effects on their target neurons, just changing the baseline state.
So if the point-to-point sensory neurons are like a private phone call, conveying very specific instructions, these neuromodulatory brainstem nuclei are like a building-wide PA system.
I love that analogy.
They shift the overall mood, the alertness, basically the background juice of the entire facility all at once.
And it is exactly that background juice, interacting with the highly specific routed data that allows the ultimate destination to do its job.
And that destination is the cerebral cortex.
Right. And most of the human cerebral cortex is specifically neocortex.
Which the book notes has a very distinct 6-layered architecture.
Yes, 6 layers. And within those layers, neurons are arranged in functional vertical columns. The most prominent players here are pyramidal cells.
Named for their shape, I assume?
Exactly. They have triangular cell bodies. They are the primary output neurons of the cortex, sending process signals back down to lower structures or across to other cortical areas.
Now, we have 2 hemispheres of this highly complex neocortex, but we don't experience reality as 2 separate streams of consciousness.
Thankfully, no.
Right, so they have to share data constantly.
They do this via a massive white matter bridge called the corpus callosum. It physically connects the left and right hemispheres.
And the text details some incredible clinical realities regarding what happens if that bridge is severed, right?
Yeah.
A disconnection syndrome.
It's fascinating. If the corpus callosum is surgically cut, which, by the way, used to be a treatment for severe epilepsy, the hemispheres operate completely independently.
Wait, completely independently, like 2 brains.
Pretty much. The textbook uses a really profound example involving language. For most people, the language processing center is strictly located in the left hemisphere.
Okay, left side is language.
Right. So if a split brain patient holds an object in their left hand entirely out of sight, the somatosensory data from that hand crosses over, like we talked about earlier, and is processed entirely by the right hemisphere.
So the right hemisphere knows exactly what the object is, its shape, its weight, all of that.
Yes, it knows all the physical characteristics, but it has absolutely no language center.
Oh, wow. And because the corpus callosum is cut, the right brain physically cannot send that concept over to the left brain to access the vocabulary.
Exactly. The patient would be completely unable to tell you the name of the object they are holding, even though half their brain knows exactly what it is.
It's literally 2 separate processing centers trapped in one head. That is wild.
It really highlights how these structures function, which brings us to how those processing centers actually store information.
Right. Memory, which is not just a single monolithic function.
Not at all. The first major biological division is between short-term and long-term memory.
And short-term memory requires continuous neuronal activity, right?
Yeah.
It relies on focused attention.
Yep. If you get distracted or lose consciousness, that electrical loop breaks and the memory is wiped out.
So how does it become permanent?
To retain that information, the brain undergoes consolidation. Shifting data into long-term memory requires permanent structural and physiological changes in the synapses.
You are physically altering the network to encode the memory.
You literally are.
And we have to categorize what kind of network is being altered, because long-term memory divides into declarative and non-declarative.
Right. Declarative memory is the what? Facts, events, remembering what you ate for breakfast, or, studying for a medical board exam.
And this process relies heavily on the hippocampus and nearby cortical areas.
Exactly. Whereas non-declarative memory is the how. It operates largely beneath conscious awareness.
So things like skills or emotional memories.
Yes. Emotional memories center on the amygdala. But non-declarative also includes physical skills, habits, and probabilistic learning, which pulls the basal ganglia right back into the picture.
The text also highlights the cerebellum's role in non-declarative memory, which honestly forced a major perspective shift for me.
Oh, how so?
Well, the traditional view of the cerebellum is that it's just a motor coordinator. Like it just smooths out our movements so we don't look incredibly clumsy.
Ah, yeah, that's what a lot of people are taught initially. But it actually drives motor learning?
Which is a huge difference.
Think about putting on a pair of prescription glasses for the first time. When you turn your head, the visual world seems to, drag or swim a bit, right?
Yeah, you get that dizzy feeling.
That's because your vestibulo-ocular reflex isn't calibrated to the new lenses, but within a day or two, that reflex adjusts perfectly.
And that adaptation is mediated by the cerebellum.
Exactly.
I really wanted to unpack the cellular mechanism behind that adaptation because it is just brilliant. It relies on Purkinje cells in the cerebellar cortex.
Yes, Purkinje cells are the key here. They receive incredibly powerful excitatory synapses from pathways called climbing fibers.
Climbing fibers, so what do they do?
When a physical movement doesn't match the intended outcome, say, your eyes don't track correctly with the new glasses. The climbing fibers register an error signal.
An error signal, like, hey, this didn't work.
Right. They fire, and that powerful burst fundamentally alters the strength of other active synapses on that specific Purkinje cell.
So the error signal literally reweights the synaptic network. It tweaks the physical software so the next time you make that movement, the outcome is closer to the target.
Exactly. It is active structural learning.
Which brings us to a really critical realization. If learning and memory rely on changing the physical structure of the brain, we have to look at how that physical structure is built in the first place.
And crucially, what happens when it sustains damage?
Right. And development doesn't just build the exact number of neurons we need. The book says it massively overproduces them.
It does. Embryonic development is essentially a brutal survival of the fittest competition at the cellular level.
Wow, really?
Yeah, tissues produce limited amounts of neurotrophic factors. Only the neurons that successfully navigate to a target and make functional connections receive these factors and actually survive.
So instead of a sculptor carefully chiseling a block of marble, it is more like building a massive, chaotic road network between cities.
That's a fantastic analogy.
And then the nervous system monitors the traffic. Any roads that don't get enough daily use are aggressively pruned back and destroyed.
Right, allowing the body to dedicate all its resources to paving and maintaining the high-traffic highways. The wiring is pruned to strictly match functional requirements.
But this highly optimized finished product presents a massive problem when an injury occurs, right?
It really does. If a sledgehammer hits that road network, we see a stark mismatch in how the body handles repairs.
Because in the peripheral nervous system, repair is robust. Like if you sever a peripheral nerve in your arm, it can often regrow.
Exactly. The Schwann cells we talked about earlier step up. They guide the regrowing axon, basically acting like a construction crew laying down detour signs to help the nerve find its original target.
But the central nervous system reacts entirely differently.
Unfortunately, yes. If you damage the brain or spinal cord, the local glia, the astrocytes and oligodendrocytes actively impede repair.
Wait, they actively block it?
Yes. Astrocytes rush to the site and form a dense glial scar. They also release inhibitory molecules that chemically block severed axons from regrowing.
So they essentially build a concrete wall over the damaged road to prevent the chaos from spreading.
Exactly, which is why spinal cord injuries are notoriously permanent.
For decades, that lack of repair fed the conventional medical wisdom that the adult brain was completely static. Like you were born with all the neurons you would ever have, and if they died, they were just gone forever.
Right, but this text outlines a major paradigm shift in that thinking.
Yeah, because we actually have adult stem cells.
We do. The adult human brain possesses latent stem cells. Neurogenesis, the birth of new neurons, continues throughout life in two very specific locations.
The first being the dentate gyrus, which is part of the hippocampal formation.
Correct. And given the hippocampus's role, those new neurons are likely participating in the continuous formation of new declarative memories.
Okay, and the second location?
It's in the walls of the anterior horn of the lateral ventricle. Stem cells there produce inhibitory interneurons that physically migrate a massive distance all the way to the olfactory bulb, basically participating in our sense of smell.
This leaves us with a truly tantalizing medical frontier for you to think about. We know the central nervous system aggressively blocks its own repair mechanisms with those glial scars.
Right, the concrete wall.
But if we have latent stem cells actively producing new neurons in the hippocampus, the architecture for regeneration actually exists.
It does. The future of neurology really hinges on whether we can coax those latent stem cells to differentiate in controlled ways.
Potentially overcoming the glial barriers to replace lost neurons in spinal cord injuries or neurodegenerative diseases.
The blueprint is there. We just need to learn the language to instruct it.
Exactly. Now, to bring all this clinical anatomy together and cement this deep dive, let's run a quick diagnostic synthesis of what we've covered.
I love a good clinical review exercise.
So imagine you are reviewing a patient's chart. The patient is unable to retain new facts, say they cannot remember what they ate for breakfast an hour ago.
Okay, classic presentation.
However, over the course of a week, they successfully learn to play a complex new scale on the piano, despite having absolutely no memory of practicing it.
Clinically, that presentation isolates the damage perfectly.
Walk us through it.
Well, the inability to remember breakfast is a failure of declarative memory, which points directly to severe damage in the hippocampus.
Right.
But the ability to learn the physical piano scale is non-declarative memory. That proves that their basal ganglia and cerebellum, the systems calculating those physical error signals we discussed, are fully intact and functioning.
Perfect. And for the second part of the exercise, if we were looking at a peripheral nerve injury in that same patient's hand, we would expect a much better prognosis for functional recovery compared to a spinal cord injury.
Absolutely.
Because the Schwann cells in the periphery will actually guide the axons back rather than forming the inhibitory scar tissue that the central astrocytes create.
Applying the anatomy to the clinical presentation like this really changes it from rote memorization into a functional diagnostic tool.
It really does. You've gone from the micro-level mechanics of myelin to the 80-degree cephalic flexure, mapped the deep relay of the thalamus, and explored the neuroplasticity of the hippocampus.
It's a massive system, but it all connects.
So next time you think about that chaotic windowless server room, remember, it's an impossibly elegant 6-layered network, constantly tweaking its own synaptic weights every single time you learn something new. Keep seeking the blueprint.